All right. So there's some seats down front, guys. If you're talking and you're just kind of chilling, maybe come down and take a listen. I got some giveaways I got to give away. I got some interesting things that I'll toss you if you can answer a question, or maybe I'll just randomly throw one at you. So if you're not awake, it's possible you could get pegged with one. Just as an FYI, yeah, could be exciting like that. So I'm going to be talking about bypassing EMET 4.1, and as one of the first kind of, I guess, who am I? Why should you listen to me? I'll do that as kind of one of the giveaways. Does anybody know the name of the class I teach at Black Hat? Raise your hand and say something. It doesn't even have to be close to being right. Okay, it's actually application security for hackers and developers. So I cover fuzzing, reverse engineering, source code auditing, exploit development, stuff like that. So if you're thinking about taking a training at Black Hat this year, maybe consider that. Anybody know when and where I gave my first talk at a conference? What year? 1901. He said 2009. He was I think it was more like 2005. At where? You got to say something if you want one. DEF CON. Yeah. Okay, so anyway, enough about me. What am I talking about today? So EMET is the Enhanced Mitigation Experience Toolkit, which is kind of the worst name ever for an anti-exploit package that Microsoft puts out for free. And this talk is not a bashing EMET talk. It's an EMET is pretty cool, and it does some neat things. But it's not, it's not the silver bullet. Hardly anything is. But this one in particular has some architectural limitations that it just is never going to be able to overcome based on the way it's built. So that's kind of what I'm talking about. I'll point out some specific things along those lines. But I think it's great for the price, which is free. So I hope you don't take away that I'm sort of bashing it. That's not what I want you to get out of this talk. But what I wanted to look at were how robust are these 12 mitigations that are offered in the product. So for every process, like, whatever, excel.exe, you can enable or disable any of these protections. And one of the great things about EMET is that it kind of takes an older system like your Windows XP and it kind of brings it up to date a little bit more toward like a Win 7, Win 8 in the sense that it has like a force ASLR, force DEP, because so kind of those are some of the modern day protections, which if you don't know what ASLR and DEP is, and ROP and gadgets and pivots and a lot of the stuff I'll mention in my talk, maybe I'll just say a couple of things real briefly, but obviously I won't have time to explain everything that's happened in the exploit development world for the last decade and a half. But ASLR is address-based layout randomization, and that basically changes the base address of all the loaded modules for a process and as well as the process itself, so that an attacker doesn't know exactly where something is in memory. And DEP marks the stack and the heap pages as read-write, so that you can't execute code on those pages, right? So one of the things that's kind of become trendy is this whole ROP attack. It's one of the newer sort of techniques that hackers use to land code on your box. And what ROP is, return-oriented programming, it's basically saying, okay, I can find something in memory, so somehow you have to get around ASLR. Either there's an old DLL that isn't randomized, or you're able to leak the base address of a DLL through some vulnerability in a product. And then once you find out where something is, you can build what's called a ROP chain, which is a series of gadgets. And what a gadget really is in 32-bit world is it's a 4-byte address that just points to some code. And what you have to do to run that code is you have to basically flip, if your input is on the heap, the stack pointer is normally pointing on the stack. It's the whole point of the stack pointer, but you have to flip that stack pointer so it points to your input on, say, the heap. That's called the pivot. And then every time you do a return instruction. That's the return-oriented program. Return takes you to an address. You execute a small piece of code like pop, pop, and then a ret. You do another return, and that takes you to the next address that's in your list of gadgets in your so-called ROP chain. Okay, so your stack pointer is moving forward like your instruction pointer used to, and your instruction pointer is all over the place like your stack pointer used to be. So it's kind of like backwards world when you're doing ROP code, basically, when you're kind of executing in that domain. So what I'm not going to cover in this talk is all the background about that, and I'm also not going to cover all the background of every one of these 12 protections that's in EMET. I was focused more on the 5 ROP protections, okay? And the reason I was kind of focused on that or interested in that is for multiple reasons. For one, I have a personal interest in it because in 2012, I participated in a contest called the Blue Hat Prize Contest that Microsoft sponsored. And what that was is you submitted your best defensive idea in terms of how to stop the ROP, so to speak, or stop some modern code memory corruption type attack. And the 3 finalists were going to get flown to Vegas and get to be on stage and do this whole crazy thing, which was really fun. So I ended up placing as one of the 3 finalists. I ended up 3rd place in that contest, and it was really a lot of fun, and it was neat to kind of help sort of make the world better, so to speak. But the 2nd place winner, a lot of his ideas are what actually made it into ROP. Those 5 ROP protections came from the 2nd place winner, and so I thought it would be fun to kind of poke a little at this, to kind of as sort of like, well, maybe you should have picked me if I can get around these 5 really easily, which turns out to be the case. So I kind of thought it would be fun from that standpoint. And of course, it's an endpoint security, basically solution, which we have an endpoint security solution at the company I work for, Bromium. So there was kind of a corporate interest there as well, right? It's kind of why we do everything. So it's great if you can sort of kind of have multiple interests in doing some research. So we wanted to take a look and just honestly be able to tell people, hey, this is great, but is it really easy to get around, or was it really hard? Was it kind of medium to get around? What like, did it take years or months or weeks or days? How long did it take to kind of bypass it or whatever? That's kind of what we're interested in. And of course, being a good citizen, just like I did the first time around when I participated in a contest to make things better. So before we started talking about this, we made sure that we gave Microsoft our whole white paper and responsibly disclosed everything, so they have an opportunity to try and address some of the bypasses that we found, which they did a little bit in the 5.0 tech preview. So 4.1 is still the current release of EMET, and right the same day basically that we talked about this, which was actually basically at our RSA in February, they dropped their 5.0 tech preview to kind of show that that this kind of coordinated release sort of thing. So that worked pretty well, I would say. Okay, so I like to have a little fun. If you see pictures that are funny, go ahead and laugh or clap or do, I don't know, buy me a beer or something like that. See this little orange guy? That means he's sad. So whenever EMET stopped me when I was doing this research, I got sad. So the first thing I tried was just firing up Metasploit and kind of trying a standard browser exploit against a system that was vulnerable to that with EMET installed to see if EMET would stop it. And of course, EMET stops everything in Metasploit basically. And that happens for really a couple reasons. Does anybody have a thought on why it's able, without reading my slide? Who's willing to say something? Why can EMET stop all the default stuff in Metasploit? Yes. It forces DEP, yeah, but true. So that's one thing that EMET can do for you. It can force DEP if it wasn't already enabled. It also does this force ASLR. So a lot of the exploits, or really all the browser exploits in Metasploit, are kind of like the least advanced browser exploits you'll run into. And so they depend on a old DLL that's at a static location. So in terms of their ASLR bypass, most of the Metasploit exploits basically just assume like msvcr71.dll is at hex address starting 7C, whatever. So they sort of cheat in terms of their ability to do an ASLR bypass. So EMET can block that just by forcing ASLR on all the old DLLs. Okay, and it could also stop it because of these 5 special secret sauce techniques that are in EMET. And that's really what I was after. I didn't care about ASLR and DEP. I'm assuming that I can get around that as part of this research. I'm more interested in the special secret sauce techniques. So that's kind of what I'm going to be talking about, those 5 mitigations. And the assumptions, again, are that I have a good bug, like the newest ones in the browser world are basically type confusion and use after free. So I'm assuming that I have a good bug along those lines, and I'm able to leak the base address of a DLL, and I'm able to generate dynamically a ROP chain and land code, and everything works great until they install EMET and these 5 special things stop me. That's kind of what I was really interested in as part of this research. How hard are they to get around? Okay, so the first of the 5 is called caller. And what caller does is it basically checks when you call a critical API. Okay, so what's a critical API? A critical API is one of these 50 functions that Microsoft has deemed as sort of dangerous to be used, like virtual protect, virtual alloc. Virtual protect is a way of changing permissions on a memory page. So if you can change the permissions on a page from read write to read write execute, for example, virtual protect is kind of dangerous in that sense. So if an attacker is able to run a payload, the ROP chain, that's what a typical ROP chain does, is it basically changes the page permissions on a stack page to executable and then runs a standard Metasploit payload like a connect back shell, or in my case, for the final demo, basically what people do is they pop a calculator. That's kind of the typical proof of concept exploit. You're basically showing that you're able to run arbitrary code on a host. So anyway, what caller does is it basically looks to see that when one of these critical APIs is called, was it called in the normal way? Did it actually use the assembly language call, or was it jumped into, or was it returned into some thing that would be kind of indicative of a ROP chain? So one of the things to notice about that already is, and this is kind of the high level theme I really want you to take away from this talk if you kind of miss all the technical bits and bytes of what I'm talking about, is that they don't really, EMET doesn't really stop ROP. It doesn't really, it basically what it is. I was trying to think of a good analogy. So if you're kind of driving down the road, and there's kind of sort of guards along the way, it's like you could be doing whatever naughtiness you want in the car until you get to the checkpoint, and then it's like we better clean up our act, right? So we can pass the checkpoint, and then you keep driving, and who knows what you're doing in there, right? And then you get to the next guard post, and it's like, oh, we gotta stash the whatever, because we're about to get searched. That's kind of how these work, really. That's the only analogy I can think of. I don't know. I'm not the best at analogies, but that's the one I'm using, and I'm going to run with that. So when we get to that point, we'll get checked. So let me just give you a little technical background. You don't have to follow all this if you don't, if you're not interested in reading code or whatever. The white paper, by the way, if you want all the details for this research, is on labs.bromium.com. The whole long, I don't know what it is, 20-page white paper or whatever. You can read all this and kind of get this if you missed this. But basically, what I'm doing at first I start with contrived problems. So I want to basically test and see individually of each one of these 5. I need to find a way to bypass each 5. And then I'll put them all together in the end in some real-world example or in a different contrived problem, whatever. But to start out with, I needed a toy problem. So my toy problem is I just had like a local binary with some simple heap overflow or stack overflow or something like that. And then I generate a ROP chain with Python. So basically, I just do like ROP gadgets, and then ROP gadgets plus equal struct.pack, and then some D word, some 4-byte address, right? And the typical thing that we're doing, in this case, I'm using virtual alloc, and then you set up the parameters, so all this data is input that you basically are reading into. So you're doing some call to virtual protect or virtual alloc to change memory permissions, whatever, and then you jump to your code, whatever your actual shell code or something like that. Because that's kind of what I'm doing when I throw that up, if you don't know kind of what that is. And I generate basically just a binary blob with Python, and then I shove that into the vulnerable program to test that I can get around each one of these 5. Okay, so that's kind of the key right there. That jump is to the virtual alloc. It's a ret to a jump. And if we run a typical payload like that, a typical ROP chain, we'll see that even without force ASLR and dep and stuff, EMET will catch that and stop that, and it'll give you actually a log in your event viewer. You'll see something like that guy right there. Let me point to it with the arrow where it says caller check failed. So that was the first of the 5, the caller check. And it gives you like the address, and when you tried to call kernel32.virtualalloc or whatever it is you tried to do, you're sort of like busted. You got to the guard post, and the guard's like, I see what you got there. Everybody out. Party's over. So that made me sad. So I had to think of a way, how do I get around that? How can we bypass this first guard? Because he kind of knows our typical trick. And, it came to me pretty quickly. Well, if the caller check is just looking to see if we're jumping into some code or reading into it, can we just find a location where that API that I would need to use is called legitimately in code, and then just call that first? Because it has to work. Otherwise, regular code won't work, right? So all I do is I basically just change the address that I go to to this 7C34A459 or whatever, which is a call, a legitimate, normal, natural call to a virtual ALEC, and that has to work. And eventually I'll hit a RET, just like I would in a typical gadget. So it's basically just kind of a slightly longer gadget than you normally see in a ROP chain. And of course, that works because it has to work. Otherwise, regular code would break. So it's like, okay, that one was pretty easy to get around. The first of the 5 wasn't too hard, so I thought, and you see that address, I changed it to the 7C blah, blah, blah 59. I just updated the ROP chain in that way. So I thought, well, maybe this won't be too hard after all. Yeah, go ahead, you got a question. You get a sucker for being brave enough to ask a question. Oh, you totally missed. So how does this sort of guard posting work is the question, I think, right? Basically what happens is those, all the critical APIs are hooked. So when you call virtual protect or whatever, it goes to like a little snippet of pre-code, and actually postcode is another one in the check we're about to talk about that basically does some, it checks the assembly of wherever you came from. It does some low-level checks basically to see if it likes the way you came to it. And if it doesn't, it raises the flag and says, nope, this can't continue, and it basically kills the process and generates a log in your event viewer. Does that make sense? Okay. It's basically hooking. If you don't know what that is, you'll have to go and look it up and figure out how our API is normally hooked. You can hook basically any call in an operating system and hook it to do whatever you want. A lot of people do that like in debuggers, like if you're trying to debug something and like you hook a certain function and say every time I hit this like crypto function, print out what the blob is before and after it's encrypted or something like that. There's a lot of interesting things you can do with function hooking. And this is just one more interesting thing you can do with it. So one of the ways that you could get around this, by the way, glad you brought that up, instead of doing the trick I did, is you could try to like jump to the actual API below where the hooking's done. So like API plus 5 in assembly, you could potentially get around its jumping. But Microsoft's done some interesting things there to make that hard, to make that less predictable, and they changed that a lot. To make that, because they know that that's like a known way to get around hooking, basically, is jump around the jump hook. So they kind of made, I thought, that doesn't sound like the most straightforward or cleanest way to do it. There had to be an easier way. So I kind of took the easy way out, basically. That's another way to, yeah, go ahead. Question back there. No, and that's one of the interesting things about these 5 special ROP checks is they're only in EMET. All the other protections that EMET offers are pretty much in the latest Windows 8.1 or whatever, like all the other, like 7, Force ASLR DAP, all this other stuff that it does. Those are like, you get all those already, but these 5 you don't get. You got to have EMET to get this stuff. And that was the other reason these were kind of interesting. Okay, so SymExec flow is basically the exact same thing as caller check, but it's the post check. After you leave a critical API, it does a very similar check to make sure that you're going to go back to code that looks legit. And the beautiful thing about that is when I was thinking about, well, how do I bypass that? As soon as I got to it, I couldn't figure, it wasn't triggering. Like I could never get this protection to like protect, because what happened is the first thing I did bypass this as well by the nature of the fact that has to work. The first thing I did has to work for this, and it has to work for this too. It's going back to legitimate code. So this is like a non-issue. I don't really even have to bypass that. That was like bypassed by default by bypassing the first thing. So there was no big deal. And it took me a minute to figure that out. I was like, I couldn't, like, I had to like dig into it a little more and figure out why this wasn't triggering. And it's like, oh wait, I'm already bypassing that. So fine. Yay. So I got my hex CC, which, by the way, what's a hex CC? Breakpoint. Who said it? Nice catch, too. Good throw, good catch. That was money right there. I learned my sports skills from my brother sitting back at the bar there. My younger brother's here trying to checking me out. He's a pharmacy guy, so he's kind of seeing what this whole hacker world is all about. He lives here in Chicago, so thanks for coming out to see me, bro. So anyway, when you're at, you see that if you probably can't read it from back there, but the instruction pointer is actually pointing to a page on the heap. And that's where the hex CC is. So when you're doing exploit development, you start by putting a hex CC where your actual shellcode would be, because exploit development is a tricky process. It's like a very delicate operation, so to speak. And so if you just try to do it all at once and build the whole thing from scratch, and throw your shellcode in and do everything from the get-go, it'll blow up and it won't work right, and you won't be able to figure out, is it my shellcode that's not working, or am I not getting to it in the first place? It gets really tricky to debug. So this kind of like is my approach to like sort of stage development, right, when you're writing an exploit. And then you look at the page permissions, which gets me a little giggly. They're read, write, execute, which is what you need, right? So that means code will execute on this page, which is a good thing. Or a bad thing, depending on how you view that. So now the next thing to do is to add real shellcode. And when we add real shellcode, we're going to end up having to bypass the rest of the stuff, right? So the third of the 5 ROP checks is this load library check. And a lot of shellcodes need to do that. They need to leverage functions and other APIs and other DLLs and things like that. But this one didn't really slow me down much because the only thing that this load library check does is basically checks to see if you're pulling a DLL from a remote share, like a UNC path or something like that. That's a naughty, no-no thing to do. But a lot of exploits don't need to do that. You don't need to. Your shellcode doesn't need to do that. So my approach to getting around this was just, okay, I won't do that. I'll run a connect back payload or some other payload, right? Or a download exec or something like that. I don't need to run a DLL for remote share. So that's not a problem to get around. And I did bump into this other thing called EAF, export address filtering, which we'll talk about a little bit when we get to another part. For now, that's not one of the 5 ROP checks. EAF is like another one of EMET's special things it does that's not normally done for you in regular Windows at all, even in 8.1 I don't think. So we need to get around that too. We'll show how we do that. For now I just tried, first of all I tried just a regular Metasploit payload. Once I got my HexCC I just replaced it with like a connect back, and it made, I was sad because it broke. And it broke at load library, and I thought, oh no, the load library check's actually like triggering, and I'm not even doing a UNC thing. And then I realized it's only triggering because we're jumping to that instead of calling to that. So it was actually the caller check that was catching me. So we just changed that to a jump instead, or a call instead of a jump. So you have to be able to basically have the ability to customize your payloads a little bit to do this sort of work, right? So if you can only run CAN scripts that you're handed, then EMET's really going to stop you because you can't ever customize anything you're doing. But if you can learn some basic stuff about how to customize some of this stuff, then you can start to get around some of this stuff, right? So you got to dig into it a little bit. So this the connect back shell worked, but when I exited, this EAF mitigation fired up and made the app crash, which didn't actually stop the payload in this case, which is odd. But anyway, what I do for now to get around the EAF protection is I just wrote a custom shellcode. And the custom shellcode just basically pops up a message box. That's all it does, with a funny little message, which we'll see on the next screen. So I updated the ROP chain to include all the stuff we're talking about. Not much has really changed. And then when I run my contrived program, which is vulnprog.exe with our ROP chain, which is this exploit.bin, then we get this message window that pops up showing that we're able to get around at least these first mitigations so far. So, you know, you got to have a little fun with this stuff, right? When you're doing it, you can't just, you know, spend all day in PowerPoint, not have fun with your pictures and things like that. So you got to go ahead and do that. So, all right. Anyway, so we got around the first 3. What about the last 2? The fourth ROP check is what's called memprot. And that wasn't really an issue for me, and the reason it wasn't an issue is because basically what it does is it checks to see if you're using virtual protect to change permissions on a stack page. So in terms of getting around that, let me see if I got any, how many suckers I got left? I only have 2 left. Anybody have an idea how I could get around virtual protect? You got to raise your hand so I can see you. I can't see you. This scale? You ready? Oh, she totally whipped on it. Okay, anyway, anybody else have an idea? How could you, like... Okay, good. Excellent. But you can have that. So, yeah, who said that? Somebody said, yeah, right there. So in terms of, you know, not changing the permissions on a stack page, you could just not, you could either not do that. You could either use virtual alloc, which is what I was doing, to create a new page on the heap. Or there may be some other deeper way to do this, which it turns out there's a way to do that too. So Virtual Protect is kind of like the top level API, and there's a deeper version of Virtual Protect called, well, we'll see that when we get there. So anyway, what I did for starters is I just used virtual alloc. I just created a page on the heap that was read, write, execute. So that was kind of like the simplest way to get around that. Or you could just remark heap pages instead of stack pages. So, yeah, we'll talk about the second one when we already did the first one. So the last of the 5 is what's called this stack pivot. And the stack pointer normally has to point to the stack, right? And if your input, your malicious payload, your ROP chain is coming in on the heap, then what you have to do is that pivot that I was talking about earlier. You actually have to change the stack pointer to point to the heap. And so when you hit a critical API, in other words, you're driving along again in your car and you come to that final guard post and he's like, hey, is the stack pointer on the stack? You got to be able to go, yes, it is. But along the road, it might not have been, right? Maybe while you were getting there, you messed with it. Okay, and that's kind of how I got around that check. Is basically my idea was, well, if my input is only on the heap and I need the stack pointer to be on the stack, I can just copy my input as like a pre-ROP chain before I run my ROP chain, basically. So my pre-ROP chain just copies my actual ROP chain to the stack, and then you can unpivot the stack pointer back to the stack. And then when you get to when you call your virtual protector, your virtualic, whatever your critical API is, then all your ducks are in a row, so to speak, in the car when you get to the guard. Okay, so this is like the newer version of the ROP chain. I just kind of keep showing it as I was changing it. So I fix the things up in the actual ROP chain, and I do the pivot, and I output it to a file. You can see the Python code to open a file and write it and close it. Not too interesting, but it might be fun if you're not a Python coder and you kind of want to learn this. This might be fun for you to play with. I highly recommend learning Python. It's a good language. And I sort of cheated because I have a contrived program, so I was able to just basically add some custom assembly to copy code around from the heap to the stack and things I needed to do as part of this, which may or may not be in the actual DLL that you leak the base address. So if you're going to do this against a real-world program, you need to actually find the gadgets to copy the stuff from the heap to the stack. In this case, I just cheated with a blob of assembly. So we'll go back and fix that later. So for now, you can see that we bypassed everything in the vulnprog heap.exe with this exploit heap.bin. But like I said, you should wonder, okay, so you got around all of them, but it was in kind of a lab environment, so to speak. It was in a contrived program. Can you do it against a real-world program? Like, could you actually, land an exploit against Internet Explorer, for example, with this technique? So that's kind of the main event, the main fight cage night sort of thing, to see if we can do that. Of course, I wouldn't be up here talking about it if I couldn't do it. Let's face that. So we need a bug, and the bug I chose was CVE 2012-4969, which is just any one of many exploits that have come out. Every browser's had exploits that have come out in the last few years. I'm not picking on IE for any particular reason. I think Firefox has had even more come out or whatever. I haven't counted lately to see which ones kind of had the most vulns come out in the last year or two, but they've all had problems. So basically just pick one, get a good working exploit, which the one from Metasploit doesn't cut it here because it depends on a static, old DLL, which EMET would stop that just on the nature of force ASLR. So that can't use that. So I got a better version from a friend of mine named Peter. He had a nice version of it that leaked the base address of NTDLL, so that you could dynamically create a ROP chain based on NTDLL. So that's what I ended up using for my exploit. And so the challenges were not ASLR and they weren't DEP because we've got all that covered. We got a working exploit. So all we have to deal with those are those 5 ROP checks as well as the EAF thing I was telling you about. And so I tried to come up with a cool picture for a bypass. I don't know. It's the best I could find. Talking about bypass, I don't know, whatever. Maybe I could have done a heart stint or something like that, or I don't know. So the stack pivot thing I talked about earlier works here too, but I had to actually find real gadgets. So basically I've got what I call a pop copy gadget, which all that does is you need a pointer that points to the stack, which in this case EAX pointed to the stack for me. And then I get 4 bytes after I do my pivot off the heap into ECX with this pop ECX ret. So all the gadgets look like that. They're like pop ret or move ret or something ret, blah, blah, blah ret, blah, blah, blah ret. So pop ret loads whatever's on the stack currently into ECX, and then I do a move, square brackets, EAX, comma ECX, which moves the contents of ECX into what's pointed to by EAX, which is a pointer to the stack. So I'm moving one D word at a time, and then I couldn't find a add 4 to EAX, so I found a inc EAX ret, and I have to do 4 of those. So basically my ROP chain becomes 6 times longer than it was, which may or may not be a problem. It wasn't a problem for me for this particular bug. The input could be of arbitrary length. So no big deal on that. So if you look at my actual exploit, which the actual exploit is basically HTML embedded with this stuff, right? So you're going to be, to exploit a browser, you're going to be hosting a malicious page, and they have to browse to your page, and there's a lot of ways you can trick somebody into coming to your page. Not only the typical social engineering, but a lot of automatic redirects from hotspots and sort of this. There's all kinds of good ways to get people to hit a page. Sort of watering hole and all that good stuff. But anyway, where you see the tab, NT DLL base plus whatever, that's my actual gadget that I need to run, and it's wrapped in 1, 2, 3, 4, 5, 6 other gadgets, and all 6 of those just move the gadget I need to be on from the heap to the stack. So you need the base address of some DLL, and you have to have found these gadgets ahead of time in order to be able to do that. Does that make sense? And then this EAF check was interesting. So the way that works, I was trying to come up with an analogy for this whole EAF thing. What a lot of shellcodes do is they need to be able to read a certain part of the DLL, and they use that for resolving base address to NTDLL or kernel 32 or something else, so that they can dynamically find and use different functions as part of their shellcode. So in terms of bypassing this EAF check, you could either A, write a custom shellcode that doesn't do that, because you don't need to do that, particularly if you already have the base address of NTDLL, which we do here. So really, if you had a custom shellcode, you wouldn't need to do that. But again, a lot of people don't. You just want to be able to use a Metasploit payload, because let's face it, writing shellcode's hard. So my approach was like, I don't really want to write a whole custom, connect back shellcode or something like that. I'd rather find a way to just disable this EAF check or bypass it in some simpler way, and then run a standard shellcode, so I don't have to create my own shellcode. And the way they sort of protect, this is my terrible analogy, the way they sort of protect the private parts of the DLL is they basically, they put a hardware breakpoint. So like, if you touch me here, I'll know you did it, sort of thing. So all you have to do to get around that is basically just disable those breakpoints, those hardware breakpoints, and then it won't know that you've touched that memory relating to that DLL. So terrible analogy there, but I was trying to come up with one that helped explain that. So basically, you just use NASM to compile this stub of assembly, which looks like a lot, but it's really not that many bytes when it's assembled. And it's basically just calling. It's using this call dword fs::edi. That's a syscall in Win7, and it's calling ntsec context thread. And it's basically just clearing hardware. All the hardware breakpoints that are set now will be cleared after this stub runs, and then you can use just any old payload you want. So that was kind of the simplest way I could think of to bypass the EAF check, which involved writing some assembly. So maybe you could argue that writing your own shellcode would have been the same hardness. I don't know. Whatever. Either way, there's different ways you could get around it. Oh, and yeah, to answer the thing I was talking about earlier, there is some deeper version of Virtual Protect. There's NTDLL, NT Protect Virtual Memory, which does the same thing as Virtual Protect, which isn't in the critical API list by default. It is if you check an option in EMET called deephooks. There's one little option that's sort of not real obvious if you're not used to using it. It's called deephooks. You can check that, and then it will also add these sort of deeper versions of APIs to the list of critical APIs. So you could, in other words, the point is that whole thing I talked about bypassing the memprot protection, that was protection number 4. You don't have to if deephooks aren't enabled. If they're enabled, then you still need to use virtualloc or some other way. But so there's multiple ways to get around that as well. So one of the things they did when they released the 5.0 tech preview is they enabled deephooks by default, which helps with this. So that was one of our recommendations, was like, you should do that. And they're like, well, we'll try it. We didn't have it enabled by default because there were some compatibility issues and stuff was breaking and things like that. That's usually why security is not as good as it could be, right? Because there's always a tension between usability and security, and they were trying to find that right line, right? Which I totally get. It wasn't anything like, oh no, they were totally dumb and didn't understand what they were doing. No, they knew that was less than optimal, but it was like we had to do this for now until some of these compatibility issues get squared away, which apparently most of those have now been squared up. So that's a little better in that sense. Okay, so putting it all together, popping the calc. So like I said before, when an exploit writer is going to give a demonstration of an exploit, a lot of times they run their exploit payload and a calculator pops up, and that's kind of the typical proof of concept to just show that you're able to run your whatever your malicious payload would be. Okay, so let me do the demo here, which is just a recording of me doing it earlier. And so this basically, all this big blob of stuff, that's the actual HTML page, which is the malicious website that you have to somehow coerce a user to visiting. And so we're hosting our malicious web server here with this python-m simple HTTP server 80. That just hosts the page of whatever in there. I run, open up Internet Explorer, and boom, get my calc. So all that proves is that the exploit I started with is working fine. Everything's working fine. So now what I do is after I close, I showed that the calc was running under IE, and I closed IE. Now I use the EMET installer to install what was the latest version, still is the latest released version of EMET, which takes a second. And then once it's installed, I basically just run the same exploit I just ran, and you'll see that it'll fail, which makes sense, right? Because EMET's going to stop it. And unfortunately, in this case, it didn't properly log. It just crashes IE. That can happen depending on what is corrupted. And that leads to the architectural thing I was kind of pointing out at the beginning of the talk, which is that EMET is basically just a DLL that gets injected into every process. So if malicious input is coming into a process at the user level and the protections at the user level, they're sort of fighting it out on level ground, which is not really what you want. You really don't want your protection fighting on level ground. So we see that EMET, anyway, EMET stopped the exploit there. And I guess I'm just showing Process Explorer. I don't know why, since Internet Explorer was crashed. And then I run the version of the exploit with the bypasses all in our exploit, and now we get the calc again. So yay, calc, you can clap. It's okay. I know we're all white people don't clap. But, can I say that? That's not true. I'm just kidding. That's not true. It's not true. I heard somebody say that once and thought it was silly. So I just repeat dumb things I hear people say. Okay, and if you can pop your calc with hex as the default, that's even more lead, I guess. I don't know. It actually just, whatever it was last is how it comes up, so it's a funny, dumb joke. So in summary, bypassing the first two protections, the caller and the symexec flow, was just a matter of reading to some legitimate code. So, or you could also try that whole jumping around the jump hooking thing that we were talking about, but that's a little, I thought, trickier. Load library, just don't use UNC pass. Stack pivot, just make sure your stack pointer's on the stack at the time of a critical API. And EAF, I just disabled hardware breakpoints. So that's kind of the summary in terms of getting around those protections. So in conclusion, I tried to come up with some nice pictures that showed the effectiveness of this protection, and I think I failed to come up with funny pictures, but it was my attempt. Look, I know how to use Google that, images, that, whatever, as well as anybody else around here. So wrapping it up, the unfortunate thing, twofold about the protection, is that it's great, it's free, it's a good tool, it's a great utility. You know, I recommend you use it, everything like that. I'm not down on it, but it doesn't actually stop what it's trying to stop. It sort of has, you know, heuristics along the way that might stop it, as long as you don't know how to customize stuff. If everything you use is canned, you will be stopped cold. Yeah, go ahead. Good question. So, and I kind of made fun of that at the top of the slide, right? So I have to be able to answer that. So the idea I submitted was kind of fundamentally different than these ideas. I had an idea that basically the crux of my idea to stop ROP was every time you hit a ret, check a whitelist of known good locations to return to, and if it's not in that list, then you just can't ret there ever. And so that that goes further. It's not perfect, because it's possible you could string together gadgets in the whitelist that would be a viable ROP chain, but not likely, because the actual legitimate call sites and a return goes back to where it was called from is pretty small, and most gadgets used in a ROP chain go to odd places in a binary that are never legitimately returned to. Like they go between instructions. Like, for example, a pivot is a strange byte. It's a particular hex byte. and it's usually between. So a move instruction is like 5 bytes, and the byte you need to pivot is usually like the middle of those 5 bytes. And you can do that in Intel x86 assembly. You can ret to the middle of an instruction and create a whole new instruction that was never really there, so to speak, but it's there by the fact that the bytes are there. So yeah, my idea was different and probably better in terms of protection, but it wasn't so great in terms of backwards compatibility. It wasn't so great in terms of overhead and stuff like that. So they had some beef with my idea, and so again, I wasn't mad that they didn't choose mine over the other. It was just a matter of them making a business decision, going, look, maybe this one's a little better in this sense, but it's not. It doesn't run as fast as this one or whatever, which isn't quite as good, but it stops everything that's canned right now until somebody releases some jackass gives a talk on how to bypass it, for example. Not that that would ever happen. I guess that could happen. Okay. Furthermore, there's other userland type anti-exploit toolkit technologies, and I wasn't going to spend the time to try to like find bypasses for all of them. But fundamentally, you can imagine that all of these technologies have the same architectural limitation. You're on the same playing field. It's not even a kernel driver that would require like a kernel exploit, like a sandbox. So a sandbox is a little better than EMET because you at least need a kernel exploit to get out of it. And a hypervisor would be even better because then you'd need a browser exploit and a kernel exploit and a hypervisor exploit to get out of a virtual machine, which is kind of what our technology is based on. So that's kind of how that sort of ties in. In terms of fixing the specific issues I found in EMET, we had made recommendations like, enable those deep hooks. Do a better job with the EAF thing. Disabling hardware breakpoints isn't hard. Maybe check more than one call deep if you're looking at if somebody's able to do this whole legitimate code thing I did. And make if possible, expand the ROP mitigations to 64-bit code because, let's face it, that's what most people are running. And these 5 special things only work for 32-bit code. So those were kind of the recommendations that went into that. And so they did. They took some of those. They couldn't address them all. They did a little bit with EAF. They enabled deep hooks. They couldn't really address some of the other ones. They also added a whole new feature called ASR, which is really confusing to me because it sounds a lot like ASLR, but they're totally different ideas. ASLR is address-based layout randomization, which is the whole changing of base addresses. ASR is this attack surface reduction, which is basically like in an Office document, do you really need Flash? And in Excel, do you really need, some a whole other technology to be able to, because they can by default. Office documents can run like Flash objects by default and stuff. So the ASR allows you to say, no, I don't ever want to see Flash run in my Office documents, for example. And that sort of gets rid of a whole mess that you might otherwise have to worry about, right? So that's a clever idea. It's something that wasn't in there previously. It doesn't really address any of what I did, though. It's just kind of a different thing that could help too, basically. Like, we've got all these things that could help too, except we're probably all bypassable, right, in some way. So many thanks to Peter and to other people that have done prior research on EMET, as well as my crew at the labs.bromium.com, the guys I work with there, and all the other people at my company, like Robert's here. Robert, say hi, raise your hand. He works with me too at Bromium. He's a smart guy. Thanks for all that, and that brings us to the Q&A. I think I'm out of suckers, but you can still ask lots of questions if you want to, and I will do my best to answer them. Anybody got a pressing thought, or doesn't have to be a question? Yeah, go ahead. Have I looked at ways to bypass 5.0? Not really, because they didn't really address so well some of the things I did. There wasn't really anything that was fully done there that actually fixes the stuff I did, so I didn't really see. And plus, my job is not to beat up on EMET, right? My job is mostly at Bromium. I'm a product security guy, so I'm like auditing our own code. We're trying to break our own stuff internally. And that's mostly what I do. And then I get to do some of the security research and speaking at conferences and trainings. So that's more like really on the side for me, so to speak. So my job is not to continually, beat up some other product. So no, I probably won't either. Like, you kicked it in the balls once, like, why go back, I mean, that's just the way I see that. Like, you got to do it again? Really? You're going to do it on 5.0? Okay, go ahead. Okay. Go ahead. No, no. I met him because the 3 finalists got like flown to Vegas and we got picked up in limo. It was this cool thing they did when we all like a couple years back when we were in this contest, and I got to play these really cool drums on stage. That was just part of it. Yeah, it factors in. Believe me, it made sense. I don't know how, but they had like a party going on at the contest where they announced what place each, because we all three knew we were finalists, but they wouldn't tell us ahead of time what place we were. So we had to like show up to get our big cardboard check, and they had a DJ like playing one of these see-through like mix boards and like E-drums and stuff next to it. And I was like, dude, let me up there. I can play the drums because I actually can. I know how to play drums. And he's like, no, dude, we don't let people. And I'm like, dude, let me up there. I'm one of the finalists. And he's like, okay, fine, come up. And I started playing with him. It was actually a lot of fun. I had a total blast doing that. But anyway, I don't think that really relates to your question. Go ahead. Next question. That was a tangent. That might have been a bunny trail. Sorry about that. It was just like one of those flashback things that came to me. Yeah. Go ahead. Next question. Somebody back here had one, but I think I missed them. No? Okay. If no more, then find me afterwards or whatever. I'll be around tonight. So cheers.